Good afternoon, everyone. Welcome. The following session, Discovering Classical Mathematics through Nicomachus, will be presented by Mr. Nathaniel Hahn, who is the upper-level quadrivium teacher at Mount Hope Lutheran School, Casper, Wyoming. Please welcome Mr. Hahn.
Does everybody have a handout? Okay, if you don't, we will be using them eventually. There's like an actual thing you can read along. We're going to do kind of a read aloud thing. So if you don't have one, find somebody to share with so that you can do that. Also, I thought I'd mention before I get started, I don't believe in karma, but I do believe in God. And when I was at college here, this is my alma mater, there were two things I avoided like the plague, and those were public speaking and being in theater. So if you get the irony here. All right. Defining terms to start here. Before we start talking about Nicomachus and primary texts, does everybody know what I mean when I say primary texts? I know this is a pretty common thing maybe in classical ed. Can you just raise your hand if you know what I mean when I say primary text? Okay. If not everybody raised your hand. Basically, the idea is these are historical texts that have influenced Western culture. If we're talking about Western primary texts, they've influenced Western culture in some way, shape, or form and have stood the test of time as historical documents that we can look back on and see, oh, this is the history of Rome or of the West, or these are ideas that mathematicians have thought since Greece until the 1500s, or what have you. We're going to talk about mathematical primary texts. Who knows, because these are a little more unknown, I think, than other subject areas of primary texts, who knows of math primary texts? Could you name one? And I'll just... Okay, Euclid's Elements. That is rightfully the most popular one. What else? Okay, yeah, Euler. He probably his most famous work is his Elements of Algebra. That's another one. Yeah, Descartes. His geometry is pretty well known. Any others? Did I hear Nicomachus? Oh, conics, yeah. Apollonius is conics. Yeah. So there are tons of mathematical primary texts, but what I've noticed is in many other subject areas, the primary texts are pretty easily focused on, right? Especially in history. You've got historians that you can read straight out of the translation and pretty much teach your class from that if you'd like. Math, on the other hand, not so much. And I'm not sure why. I've been thinking about why this is. I think there are probably two main reasons why. The first would be that they seem outdated. And I know this is a common argument against all primary texts, but mathematics is a science, right? We could say it evolves over time. At least we like to think that. And as new ideas develop, you start seeing the older works, Euclid's Elements, Nicomachus, anybody, as outdated. We've discovered more math since then, so maybe these older guys are less important now. Maybe we should only be reading up on the bleeding edge of mathematics. I'd like to make the argument that that is not the case. These texts are very relevant to us. And then the other reason why I think they're not used as much is because they're inaccessible. And I think this is in large part true, because we don't have easily accessible editions of many primary texts. Thankfully, Euclid's Elements is one that's very widely accessible. It's the most printed book in the world next to the Bible, historically. And we have lots of educational resources on that too. But that's about it, as far as I know. There are probably some that maybe you know of that I don't. But I think even though these texts aren't accessible now, we would do well to make them accessible, and we'll get to that too. But there's the rationale for this talk. I'm going to tell you how generally, how these primary texts can inform the way we teach as is. So you wouldn't necessarily need to read all the primary texts to get benefit out of this, or even necessarily teach a text directly. But I'm going to tell you how these can inform the way that we teach. And then we're also going to take a look at one specific primary text, Nicomachus' Intro to Arithmetic. I really like this one because it's short. You could actually read through it with a class in a school year with not much class time. So we'll talk about that. I've got a few chapters of it in your handout here. We'll get to that later. We'll do kind of a workshop thing going through that. But first, let's talk about, in general, why are these things useful? How can they inform the way that we teach math? So first, you can see on your outline here on the front, the reason why these things are important. First is because they are written in language. Now that might sound redundant, like isn't everything written in language? But turn into your handout for a second. Does this look like your average math book? There's very little actual number written here. There are not many symbols written here. The reason for this is, well, it's more settled in language than your modern math textbook would be. I'm not saying modern, I'm not ripping on mathematics textbooks. They're great. They help teach methods and concepts and things like this. However, you cannot have an actual mathematical thought without language. You cannot be outside of language. And I'm seeing some of you thinking, is that really true? I want to define terms here. I can imagine things without language. You're probably thinking, oh, I can picture a square in my head, right? And I don't need to necessarily think square to have that image. But can I talk about that? Can I think about that square? Can I reason about it without language? No. And if you have arguments against that, we will have time for questions. And maybe we can talk about that. Your outline is actually out of order. That was your second point. And you'll find, I say language is the natural human way of thinking. Even if you were to disregard my last comment, you could at least agree with me that speaking in plain language is generally more easy to understand than if I were to write some algebraic equation on the board, right? Unless you are a math person. So, primary texts in general, at least up until 1500s-ish, they're all written in prose, basically. And this is something that I think we can imitate in our classes, even if you're not using primary text. This is something that we can learn from because, say I'm teaching a lesson, let's take algebra, and I'm talking about, like the equation, you just have to pretend I have a whiteboard here. 2x plus 2 equals 10. Okay, I could just say that, and then I could do what I've seen some professors do. You just kind of write the next step, write the next step, write the next step. Maybe explain the process you're going through, but not actually describe what does 2x plus 2 equals 10 mean. And what I'm actually asking here is, what number, when I multiply it by 2 and then make it 2 greater, is going to give me 10? Now, I know that to us that seems redundant, but to children I've found, and to students, that this actually makes a huge difference in how they see that equation. And this isn't just for algebra, this is for anything. So, language's natural human way of thinking, this is something we can learn from even if we're not reading an actual primary text. Second, and this is first for you on your outline, primary sources are very good at making definitions for mathematical ideas. We might have this in some regard in the way that we all teach math now. Rational number is an integer, anything that can be expressed as a regular number, an integer over another integer. That's a definition. But and we'll see some of these hopefully in Nicomachus. But I'm going to give you some examples of definitions that are in these classical sources that really make you think more about the nature of the mathematical objects you're actually talking about. Because often when we're teaching math, and I'm guilty of this myself largely, when you teach math, often you can find yourself teaching a method, which I think we can all agree math isn't just about teaching methods, right? What's a more diabolical thing that can slip in is you'll often say, well, I don't want to teach the method, I want to teach why this method works. Now that's great too, because you don't just want kids to be blindly going through mathematical algorithms, but what is the object of what you're explaining? Even if you're explaining why a mathematical method works, the object of what you're talking about is still the method. What I'd like to tell you or explain to you is, and how these texts operate, they're not so much focused on methods. There are methods in these works, but their main focus is the mathematical objects themselves. You can think they're what is questions. So what is a number? What is odd? What is a prime number? What is division? Okay. These are questions that I think we need to ask our students and explain more. And this is something I think we could all do better at. And it's something that I have also found is extremely beneficial for my students' understanding. And I think it would be for yours as well. I'll give you some examples of definitions that we get from some of these primary sources. First, I'll give you my favorite one. It's from Euclid's Elements. So you can thank Euclid for this. And that's his definition of ratio. Euclid's definition for ratio is this. A ratio is a relationship, and I'm paraphrasing here. It's a sort of relationship according to size between two magnitudes or two things. Now, raise your hand if you think that sounds like a pretty decent definition. A ratio is a sort of relationship according to the size of things between two numbers or magnitudes. I'd like to point out to you, though, that in this definition, and this you get these all over the place in primary sources. If you look at the word that Euclid uses for ratio, that word is logos. And your mind should go to, oh, logos actually means word. It has to do with making connections between things. It has to do with communion between things. If you understand that sense of ratio, all of a sudden the idea of ratio broadens up and you think, oh, a ratio is actually any sort of way that I can speak of a relationship between two things. And this is true for words in general, but specifically in math, this could be what we think of as ratios. It could be an algebraic equation. It could be something that isn't traditionally taught anywhere, but it still explains a relationship between something. And by the way, historically, algebraic equations were seen as ratios, just very complex ones. I think that's pretty cool. One from Nicomachus. Here's one that you could use with third graders whenever you learn even and odd. So what's the definition of even or odd numbers that you've heard or that you learned? Anybody have one? Okay, evenly divisible by 2. I like that definition. Any other ones? I think that's usually the way it's described. A more algebraic one, more technical one is it's any number that can be described as 2 times a number, essentially the same thing. Nicomachus describes it like this. Even numbers can be split up, again I'm paraphrasing, they can be split up into two equal groups. That goes with our definition. An odd number, though, he doesn't say it's just a number that can't be divided into two equal groups. He says an odd number is one that can be divided into two equal groups with one number left over in the middle. That changes the way that you think about even and odd. It almost makes odd numbers not quite sound so odd. I could go on, but I think I'm going to move on to the next point here, because I want to leave time for us to be able to actually read this text. So we've got the language thing. Primary texts get us in actual language. They've got us using plain words to, well, sometimes not so plain, but words to describe mathematical things, mathematical ideas, mathematical objects. On the other hand, the place in history of primary texts and the philosophies of mathematics that the primary texts present can also inform the way that we teach and the way that we present ideas. And I'm also going to give you examples of these. Here's one historical example. The difference between quality and quantity. Who has heard of this before? Quality and quantity. This is an idea from Nicomachus. Other people too, but we're in Nicomachus land right now. So, okay, so classically speaking, quantity is something that has to do with how many things I have. It has to do with addition. I can keep stacking more and more things on top of themselves. Quality has to do with what we would think of as multiply-ish stuff. It has to do with the characteristics of a number as it is. So I could say that a quality of 6 is that it has a factor of 2 and a factor of 3. Not so much the idea of counting. This is something that kids don't get taught necessarily from your average textbook, but it's something that comes in very handy. For instance, I actually tested this out with my 6th grade class last year. I was teaching them fractions. And I didn't use the words quality and quantity, but what I did tell them was, if you have two fractions and you're trying to add them, the type of fraction has to be the same. You're all familiar with this idea, yeah? You have to be adding fourths to fourths or sixths to sixths. You can't add, and this is the thing that I told them, you can't add two different things to each other. You can't add different things. So essentially, you have to have the same quality of numbers to be able to add them, which is a quantity type of thing. And I found that this made the idea click for them, rather than thinking, oh, I can add 1/6 and 1/4, but I have to get common denominators. Rather, if you think of it as, I actually can't add 1/6 and 1/4 because they're different things. 6ths and 4ths are different things. I have to change them somehow to make them be able to add. Change them to a different quality of thing. I don't know, that made it click for some of them at least. Let's see here. Okay, here's another big one. What are some things besides fractions that you find kids often say they got stuck on, or that adults say they got stuck on? Has anybody? Okay, percentages. What else? Long division. Okay, yeah. Trig. Okay. Anybody heard algebra as well? Like, oh, math was great until I got to algebra. I actually heard, I can't remember who it was, somebody told me math was terrible until algebra, which was kind of cool, but usually it's the case. So I've got a couple examples for you. Ratios, division, fractions. Those go together. And then algebra. Both of these points, when you understand them historically, can actually affect how you teach them and make it easier on your students. First, ratios, division, and fractions. Historically, and I'm talking like Greek times, so maybe we could say, I'm not going to give you dates because then I'm going to get in trouble with the historians, but we could think like 200, up to 200 AD or something like that. One, fractions were not seen as numbers. They were seen as practical ways that we can talk about like actual objects. I need a half of this stage, or I want a third of a serving of flour. But when you actually talk about what numbers are, they would say, oh, fractions aren't numbers. They're basically coping mechanisms for real life. But when we go through the normal, order of math, and first you teach the kids, okay, what are numbers? 1, 2, 3, 4, 5, and then eventually you get to the number line, right? And then kids learn, oh, actually there are these other numbers, which is kind of cool. Like, oh, between 1 and 2, there's actually another number. There's 1/2 or 1/3. Well, that's not between 1 and 2. That's between 1 and 0. And then later, you get to these ideas of there are numbers that we can't even express using numbers, like pi. But they're still in the number line. So what happens is our definition of number starts at a very natural stage, which is how the Greeks saw it. And then as we take kids through math, they start going through history and start seeing, oh, actually fractions are numbers. Well, later in history, guess what? Eventually, mathematicians start accepting fractions as numbers. Negative numbers came a little later. 0 came in somewhere there too. And then we also get the acceptance of irrational numbers. This all came around 1600s. And the fact that this didn't come until the 1600s should tell us something. That if it took the best mathematicians of history to get to the idea that fractions are numbers, and there were heated arguments about this, then we shouldn't necessarily expect a third grader to understand a fraction is the same thing as 1, 2, 3, at least not right away. So I would suggest, and I don't have answers necessarily for how this should be done, but I am trying to get you to ask, should we be teaching fractions as numbers? Should I teach pi as a number? Or should I teach it just as a ratio? These are the kinds of things that math history, and if you get these in the actual primary sources too, at least the ones that I've read. I haven't read as many as I'd like to in the future. But these are the kinds of questions that get brought up when you start looking into math history and the primary sources. One more I'd like to talk about briefly is algebra, and this also has to do with the history of math. What I've often seen is that Algebra 1, you're talking mainly about, who all teaches algebra in here? If there aren't, okay, there are a lot of, if there weren't a lot of you, I wasn't going to bore you with the algebra, but there are. So, Algebra 1, you're basically dealing with what? Solving simple equations, maybe systems of equations. You get some word problems in there, right? Algebra 2, you take a switch, you take a turn, and you start talking, and maybe you get like graphs of equations, or you start that. Algebra 2, you start talking about things like polynomials, and how, you can actually, speaking of long division, you can actually divide polynomials by binomials. What does that mean? You can graph equations, and they look like these cool swirls. What's the connection here? And I think there's a historical disconnect here. Pre-1600s, so we're talking Greek times again, you did have algebra. But again, your definition of number was 1, 2, 3, 4, 5, etc. And when you do algebra in Greece, if you ask a question like 2n equals 11, 2 times a number equals 11, they would not say the answer is 5.5. They would say you asked the wrong question. Compare that with post-1600s. This is after people like Descartes, who reinvented what algebra means. Now, you ask a question like, if I ask the question, square root of a number equals -1. Okay? Now, post-1600s, people don't just say, oh, that's a stupid question. They actually say, numbers aren't just 1, 2, 3, 4. Numbers are actually symbols that represent whatever I want it to. So now, all of a sudden, you have things like square root of -1, or imaginary numbers, or irrational numbers. And again, we are asking students to take a jump from a very natural understanding of numbers, and then really without telling them, or maybe some of you do, but I haven't really, and you take a jump and you say, oh, wait, now numbers are just symbols? You know, you hear people make the joke like, oh, I liked math back when it wasn't just a bunch of letters. Well, there's actually a truth to that. They like the old Greek stuff, and we're trying to force on them the post-1600 letter stuff. Now, I'm not trying to trash modern mathematics, by the way. Look at all the stuff we've been able to do because of it. But I am saying we need to make these distinctions in the classroom more than I think, well, more than I do anyways. Okay, so those are some examples of benefits of primary texts, how they can form the way that we teach math. I'd like to actually get into what it would look like to teach a primary text directly, and then we should have time for questions and comments, etc. So hopefully, if you are below high school teacher, you can apply some of this stuff yourself. Even if you aren't going to teach primary texts directly, I would tell you it's still beneficial to read them. I also don't want to say you have to read them, especially if you're like a third grade teacher, because you have to teach 17 different subjects at once. But I am saying if you do have the time, these kinds of things can be very beneficial. And I'm also hoping to convince you that whatever the case, these kinds of texts do need to be more included in future math curricula. The ideas in here need to be. The idea of we need to start using language more. We need to understand math in a more historical context. So, let's take a look at an actual chapter from this, because I'm talking this up and you don't actually get to hear it. So, I'd like to go to page 52. Sorry, I didn't reorder the page numbers here. It should say chapter 3, the shape of ratios. This is not Nicomachus' title, but it is his chapter number. This particular book, it's what it says. It's an introduction to arithmetic. He goes through all sorts of relationships between numbers, all sorts of kinds of numbers. So you get prime numbers, you get all sorts of a 2 to 3 ratio, a 2 1/3 to 1 ratio. You get things like prime numbers. You get things, did I say that? Perfect numbers. Even and odd. It gets very philosophical. It's kind of cool. But let's go through chapter 3. And I'm just going to treat you kind of like you're my class, just to give you a demonstration of how could this actually be done in the classroom. And I did this past school year with my high schoolers, and it worked pretty well. I don't know how it would work with 8th on down. I haven't tested it. But I will say these kinds of things work good as read-alouds. Don't expect the students to read these on their own, because the language, as you'll see, is kind of weird without explanation. Okay, so here's the introductory paragraph. Nicomachus gives us an interesting triangle involving the double ratio, so times 2. Traveling across the triangle, you find the double ratio. Traveling vertically, you find the sesquialter ratio. There's one of those numbers. It just means a 3 to 2 ratio. And traveling diagonally through it, you find the triple ratio. So I'll just read this through to you. Every multiple will stand at the head of as many superparticular ratios corresponding in name with itself, as it itself chances to be removed from unity. That's his word for one. And no more or no less under any circumstances. And what he's saying here is, if you look at the triangle, and he writes this triangle in his own manuscripts. So does everybody see you got the double ratio on the top? Just keeps timesing by 2. On the side, on the bottom diagonal there, he's got 1, 3, 9, 27, 81. What he's saying is, corresponding to how many multiples of 2 you have, going down the triangle, you have the same number of 3 to 2 ratios. So take a look, for example, at 4. That's the second multiple of 2. How many 3, it's upside down, but 2 to 3 ratios do you see? Well, 4 is to 6 is 2 is to 3. 6 is to 9 is 2 is to 3. You get 2 rounds. Okay, so continuing on to section 2. The doubles then will produce sesquialters. The first one, the second, 2, this is a little confusing. The first, 1. The second, 2. The third, 3. The fourth, 4. The fifth, 5, etc. Neither more nor less, but by every necessity, when the superparticulars that are generated attain the proper number, that is, when their number agrees with the multiples that have generated them, what I was talking about before, at that point, by a divine device, as it were, there is found the number which terminates them all, because it naturally is not divisible by that factor whereby the progression of the superparticular ratios went on. In other words, the number that you end up with, so if we start at 4, the number we end up with as we keep going 2 to 3, 2 to 3, 2 to 3, will have just as many 3's in it as we started with 2's. So there are 2 2's in 4, there are 2 3's in 9. Is everybody tracking? Or is this like totally weird? Sorry, he's talking multiplying. So 2 times 2 is 4. 3 times 3 is 9. Yeah. I'm going to skip ahead a little bit here. He's going to explain it here. As an example, since doubles generate sesquialters, again, 3 to 2, corresponding to them in number, the first row of multiples will be 1, 2, 3, 4, 8, 1, 2, 4, 8, 16, 32, 64. Now, since 2 is the first after unity, this will be the origin of one sesquialter only, 3, which number is not divisible by 2, so that another sesquialter might arise out of it. So I might explain to the class that if you think of 2 as a storehouse of 2's, there's only 1 2 and 2, and when you apply the 2 to 3 ratio, you lose a 2, you get a 3. So you only get 1 round of that. If you have 4 2's multiplied together to get 16, how many times can you do the 2 to 3 ratio? 4 times. Lose a 2, gain a 3. 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 And you're walking down this triangle as you go. I'm going to skip ahead here. So he goes on to explain more of it, and I would go more into that with a class. But what I'd like to point out to you here is I would then have questions at the end that are like concept review questions, assess, are they understanding the content? And then we would have time to talk about what we read. Any questions on that so far? I'm curious, does that make sense to you all or not? Or should I explain something further to you? Yes?
I mean, I'm struck that the wording, it's not vocab words we use. So like if you're teaching it, do you use different words or do you take a lot of time to define the words that are not common to use?
Good question. And I'm realizing as I'm reading this to you that I did make a mistake in not showing you earlier chapters, because if you'll notice at the top, this is book 2. They would be very familiar with what the sesquialter means by now. So I'd probably remind them at that point, like, remember sesquialter is the 3-to-2 ratio, but they would have experienced this multiple times. And actually, Nicomachus goes into very minute detail as to describe what the sesquialter ratio is. It's the whole chapter, basically. Yes?
It also strikes me that Nicomachus, I'm sure as well for Euclid, that these aren't counting things.
Mm-hmm.
He's not thinking of calculating, counting. He's really thinking of them as like a substance, like there's a threeness.
Yes.
Three thing.
Mm-hmm.
Very, very abstracted mind, and yet he doesn't, he really just wants to investigate the pattern.
Yeah, and he makes it tangible. He actually sticks it in a triangle and shows you visually. But yeah, that's the quality quantity thing. Like you can either look at numbers kind of in themselves, or you can stick them together. I like to tell my students, and this comes from ideas from Nicomachus. Adding is sticking things together. Multiplying things is mixing them. So if you think of sticking things together, they kind of have to match, like Lego bricks. On the other hand, you can't really stick together a Lego brick and an orange. However, if you're multiplying, you can mix things. So you can do things like multiply a foot and a pound, and you get something called a foot-pound, which is a different unit in physics. Or you can multiply different fractions. You can multiply a sixth and a fourth, and you get a 24th. So there's a sense of mixing, and you get this in the triangle too. You can see, for example, under the number 4, you get 6. So if we kind of stop halfway on the journey down to the triples, you get this number 6, which is a mixture of 2s and 3s. It's 2 times 3. Or if you go down to, if you start at 16 and go down a few, you get to 36. Now I have to do math in my head. That's a certain number of 2s and 3s, 2 each. I think it's 3 2s and 2 3s. 2 2s. Yeah, so anyway, it's a mix of 2s and 3s, right? So you get this multiplicative mixing versus additive sticking together. And I've also found that description of how numbers interact has also been very beneficial for the younger guys. And for the older guys too. Like you can't add x squared and x together. It carries through to algebra as well. Yes? Yeah, and in fact, it's not in here. In the next chapter, he starts with the triple and the quadruple, and he shows, oh, actually, you get the same thing when you do it this way. Yeah, that's super cool. Yes?
Back to also the younger ones. Have you ever thought about multiple tours through, like at a younger grade, they might just have the triangle and fill in blanks, and they could find patterns in order to investigate the blanks. It could be a contest or made into an activity that inspires some curiosity about the triangle, and then later they come back and get more of the vocabulary and the actual text.
Yeah, that's a super good idea. This goes back to like accessibility. That would be awesome, but we don't have something that does that. So right now it's kind of up to us. Like, okay, I want to pull this idea and put it in my 3rd grade classroom, and that'd be a really fun game. And they'd learn that quality idea of how numbers can be mixes of other factors. Any other questions or comments? Yes?
Can I just ask how you logistically work this into curriculum, or do you not want to talk about that?
Yes, I will get to that. I'll have time to get to that. Good question. We'll get to that in a second. Any other questions about what we've talked about so far, or comments from your own experience teaching math? Okay. So, yes, in answer to that question, I'd like to tell you how I've used this and how you potentially could use this actual text in your classroom. So, what I've done is, and you can actually take a look, I've got an actual full copy of this. I've formatted it for use in the classroom for free if you want to use it. And I used the whole text last year. We went through almost the entire thing. And what we did was had a separate Friday class once a week, 45 minutes, because our Fridays we have like a different Friday. It kind of interrupts the pattern. And I had a 45-minute class where I'd do a couple chapters of Nicomachus. Now, you may not have that, but I've formatted this so that even if you just take 45 minutes to a half hour at any point in the day, maybe as a replacement for a math lesson, I know that that's hard to do because those days of math are precious. But maybe there are some lessons that you find don't matter and you want to supplement it. So you could maybe plan it. You only need one class a week to get through this, and it works pretty well. There are this particular thing only takes 22 weeks if you do 2 chapters a day. So you can spread that out if you want. I wouldn't recommend condensing it to more than 2 chapters a day. So let's see. What else did you ask? Yeah. So that's how I did it. If you would like to download this curriculum and print it off, I don't have it available for on-demand printing because I don't have a publisher or anything. But you can either email me or you can visit that website on the bottom. And I'm sorry, right here, Stoicheia Math. And I've got this resource right there for you to download as well, if that's something you'd either like to read for yourself or use with your class. Yes?
I might also point out that you have a teacher edition on it.
I do, yes. Thanks for pointing that out. I've got a teacher edition. It's got answers to all the questions. I've written review questions for every single chapter in the text, aside from the ones that I've kind of moved to the appendix because they get a bit too technical. So as a teacher, you don't have to figure out any of the answers to those questions. You can just know those answers via answer key. A couple other footnotes. But yeah, there's a student and a teacher edition, and you can download both of those for free. I realize I went a little faster than necessary. Does anyone else have any more questions? Otherwise, I'll give you a couple more recommendations for texts you could read, and then one more resource as well. Any other questions just on content that we've been talking about? I see 1, 2, 3. Yes?
Can you give an example of how you would do this with Euclid? Like, are you going through the propositions and actually doing them?
Yeah.
Or just walking through them?
There are people more experienced than I am with Euclid. I have gone through some of Euclid. I did books 1 and 2 a couple years ago. What worked for me and what I've heard works for people is, yes, go through them. Don't have the kids try to figure it out for themselves. Read it like a text. Work through the construction on your paper as you read it. I've also heard what works well, and I also did this and it worked pretty well. Have a student each day be the presenter and actually prepare beforehand, do it on his own, and then come up and go through the propositions with your guidance. If they make mistakes, then you can correct them. But like I said, there are people who have done all of Euclid in a year, and I have not. I'm not sure how they do that, but if you email me, I might be able to get you a couple people too. Okay, yeah. Yes?
I'm curious. I really like the kind of the distinction between the pre-1600s and post-1600s math.
Mm-hmm.
But eventually we need to get to the post-1600s math. I'm curious, does this slow down the path, even though it lays much better, groundwork to actually understanding what comes later? I mean, overall, does it take longer to do it this way, or do you find it's still comparable, just with maybe a deeper understanding?
My main answer is I don't know, because we all work with curricula that follow this pattern. And to stop gets us behind. I will say that I teach Saxon right now, Saxon math, and in any given year we get to about, this is probably familiar to you math teachers, we get to probably lesson 80 or 90 out of 120 by the end of the year. And I have found no problems with that. That's partially because of how Saxon comes back and reviews stuff over and over. But I will say, and I think this is true of other subjects too, it's better to dig in deep with the topics that you're teaching, and maybe it takes longer. So the patience there is better in the long run than saying, I've got to reach lesson 120 by the end of the year. Because then you're just going to leave kids in the dust. But, yeah, I'm honestly not sure if doing something more primary text-based would slow them down or not. I think that's something that hasn't really been tried, but worth trying. I think there's a slight leap of faith that we do need to do if we want this kind of integration of primary sources to be more mainstream. Yes?
You said you did this with your high schoolers. Which ones? What classes?
Our school is small enough that it's all of them.
One. Okay.
Yep. And you get different levels of engagement. You've got the kids who really like math, and they're all in it and loving it. And then there are the kids who don't like math, but they're still tracking, getting along with it, and probably they pull away some neat stuff.
But like what class were you doing this in? Like what course material were you doing this in conjunction with?
So this was just like a separate class.
The other math class.
Yeah.
All had that one.
Right. We had a separate time set aside for primary math text teaching, and that would be probably if you were to incorporate it in an actual curriculum. Like, oh, I'm an Algebra 2 teacher. I want to teach Nicomachus on the side. It'd probably just have to be your 10th graders or whatever. But I'd probably recommend, if you're reading through this, I'm thinking high school. As you can see, the language gets a little tough, unless you got really well-read kids. Yes.
With all of the high schoolers together, regardless of what their mainstream math class was, did you see any difference or regard for prerequisite knowledge? Or was this accessible? Was this work accessible to all?
I would say that this is for sure accessible to a kid who's had at least Algebra 1. Potentially, even not Algebra 1. Sometimes the algebraic teaching almost gets in the way of understanding the Greek way of thought. But I didn't have 8th graders, and by the time you're a freshman, you've probably had algebra. So that would be something I haven't really tried. Potentially, with enough explanation. Yeah. Yes?
Yeah, classical education, I've done a lot with the Caribbean.
Mm-hmm.
Music and astronomy. So I'm really excited about this, and I'm seeing it, but I looked just on randomly on the first page of this, page 32, chapter 60, numbers.
Yes.
To see the real liberal arts dimension of this. You said math is a science. Well, it's a liberal art.
Yeah.
Probably too, but on that first paragraph, it talks about perfect numbers with equals always considered as a mid-ground between greater and less, and isn't the word moderation between excess and deficiency. Well, let's get this into ethics, into the Nicomachean ethics.
Yeah.
And then this one, and that which is in tune between pitches too high and too low. We look at them apply music is mathematical. And to make that connection between math and music opens up so much and ties together so much. He's using aesthetic language, number 3. It comes about that even the spare and excellent things are few and easily enumerated, while ugly and evil ones are widespread. So also the superabundant and anyway, the aesthetics, like there's a math to aesthetics, to again the connection between arithmetic and music, and even ethics. And this idea of the mean between extremes is really quite striking, and I'm excited about what you're doing with this, and it has a whole lot of potential to add really important dimensions to this rediscovery of the classical liberal arts. So,
Thanks. Yeah.
absolutely.
Well, thanks. So Nicomachus has a chapter completely on music. Yes, and I wish I would have printed the table of contents, because you get a chapter completely on music. You get a chapter on the quadrivium, actually. He goes through all four liberal arts and talks about how they're connected. This comes from Nicomachus. So Nicomachus is a Pythagorean, it's a philosophical group of people from ancient Greece. And math was basically their religion. It influenced Platonist thought, so it influenced Plato, and it went on to influence math for a long time. So the fact that the guy writing this has a very holistic view, his religion is math, so he sees math everywhere. Music, astronomy, he sees it in morality. To see someone with that perspective, it's not good to be a Pythagorean. They're theologically pretty bad, but philosophically very interesting and useful. They have a lot of good ideas, and to read someone who has that kind of idea really changes the way you see math as the more holistic. You see it in music. You see it when you look up in the sky. You see it when you point from here to here. Oh, that's trigonometry. So thank you. Yeah, I love that about Nicomachus. He's awesome. Yes. Right.
You also have to, would you say you would start out using the vocabulary and the language laid out in Nicomachus or Euclid, and then translate that to the modern lexicon, or would you start out with modern math and then introduce this to enrich it? How would those two different definitions combine together?
Yeah, that's a very important question, because the words that we use are not interchangeable. If I say ratio, that means something different than division, even if our conception of the idea is essentially the same thing. So to decide, am I going to say sesquialter, or am I going to say 3-2, that's a question that, number one, I suppose it depends on what you're trying to teach. In that particular example, sesquialter, you could look at the etymology, and I'm trying to think. I'm not a Latin teacher. Is that even Latin? Sesquialter. Is alter Latin? You're the Latin guy. Okay, yeah, so a half and another. So in one sense, yeah, that's 3-2. But, and that's the way he speaks of it too. It's a half and another. He almost thinks of it additively there. Which does help with ratios too. If I want to take the sesquialter of 4, I'm going to take a half of 4, which is 2, and then another 4, which is 6. And you end up with a 3-2 ratio. So at the very least, there are ideas that you can find in the actual words that are helpful that you wouldn't get if you translated it. But also, you're right, there is just the fact that we live in the modern day and people talk about numbers, and kids have to know how to actually they're not going to, they're just going to be confusing to their coworkers if they say, oh, I need the sesquialter amount of, right. So yeah, there are benefits to both. But yeah, I think that's something that consciously needs to be thought about. Same thing with ratio. Like, you lose the logos word there, which is very interesting to me, and I haven't fully dug into that, but it gives you the sense that ratio is a very, very central idea to how numbers behave and interact. I saw another hand. Yes?
I was just going to say that I used Nicomachus to explain creation and the fall, because the goal of being is perfection. And in nature, if you live at perfection, things survive that will destroy you. So I'm also in the bottom. And so at the perfect goal of being, bacteria survives that could never survive otherwise, and it's very dangerous when a grower gets that perfect mean. So there's actually a perfection in the excess and the loss, under the line, above the line. And we see it in nature when we have a dry year and then a wet year, which allows different things to survive, and it balances out. And it becomes very philosophical, and it's a beautiful example of what God did by setting the world off just that little bit, and yet still achieves life.
Yeah, isn't that amazing? And all that wrapped up in talking about means between things. It's pretty crazy. Yeah.
I just wondered, would you say that our modern or contemporary way of instructing in mathematics removes the relational and qualitative aspect out, and that's diminishing?
Yeah, that's an interesting historical thing, because on the one hand you can talk about the philosophy of math as mathematicians have understood it, that are doing the mathematical research and that kind of thing. It's another thing if you talk about the history of math education. Interestingly, math education has, for the most part, always been emphasized in times of war, where you need physical shields to protect from flying objects, things like that. Or if you have a time in history where engineering projects are very important. And in either of those cases, it's a very utilitarian look at, we need to get students to understand how to calculate this or that to get a maximum result. I don't know of many times, and I haven't read a full span of math education, but in some respects, I think this kind of thinking has often been reserved for the mathematicians doing the philosophy and not for the classroom. So is it getting worse? I don't know. I think I would need to dig more into the history of math education in particular. But regardless of if it's getting worse, it could definitely get better.
So just a follow-up, and one of the ways to get back and reasons for doing this would be to draw out the beauty and the harmony and the proportionality.
Yeah, for sure. Because, once you get into the language of the stuff, language connects everything. Instead of just talking about 2's and 3's and x's and y's. Now you're talking about, in a broader scheme of things, actually, I use the word mean when I talk about the golden mean and how things can be properly balanced, like in Nicomachean ethics. So yeah, definitely. I think what am I supposed to be done at the half hour? Yeah, now. I can take, if you have more questions, I'm happy to stick around and answer them, but thanks so much for listening.